Hi everyone. If you're working with Azure, there are two frameworks that you need to get yourself familiar with. The well-architected framework and the cloud adoption framework for Azure. Those two frameworks are designed by Microsoft, when used together, provide a full set of guidelines that allow your organization to successfully adopt the cloud and successfully architect individual solutions. Before jumping into the well-architected framework, which is the subject of today's video, I'm going to take a moment to talk about the cloud adoption framework, also called CAF, and explain how it comes into the picture and why it is used together with the WAF. So if we think about adopting the cloud at organizational level, we can imagine that this is a pretty significant undertaking. So it requires us to follow a proven set of steps or phases to increase our chances of success. The CAF is essentially Microsoft's point of view that they have acquired through experience with working with many clients of what is the life cycle that an organization should follow to successfully adopt Azure. So this life cycle includes a few phases, starting with strategy. Strategy is where the organization decides what are their motivations to move to the cloud, what is the return on investment they're planning to get out of the cloud, etc. Once they have done that, they move to a planning phase where they plan what skill sets are required, how they're going to align their entire organization, they plan for DevOps, etc. Once this is done, they can start getting ready, which includes preparing the development environments, landing zones, and all that. And once this is done, they can actually start adopting. Across all those phases, there are two things that the organization needs to do all along, which include govern, manage, and secure. So this life cycle is the central concept around which the CAF is developed. Obviously, it goes in detail in each of the phases, it tells you what to do, etc. It gives you practices and methodologies that you need to follow. But when we think about the CAF and the adoption lifecycle across the organization, we come to the conclusion that this top-down kind of adoption strategy or adoption lifecycle needs to be put in place by central teams within the organization. So the teams that will be primarily using the CAF are central teams, which will include, for example, cloud operations, DevOps, security, cloud financial operations, platform engineering, okay, there may be some others, but those are the core teams, and your organization may or may not have all of those teams. Some of those things may be actually part of a larger IT teams instead of dedicated cloud teams. For example, you may have your financial operations at IT level versus cloud level, etc. But the idea is that it's those central teams that will be mostly referring to the CAF in order to successfully implement the cloud adoption lifecycle. When we talk about the well-architected framework, or also called the WAF, first we need to start by talking about central concept within the WAF, which is the workload. Because in the WAF, everything sort of revolves around the workload. And the workload is essentially a collection of components and processes. So components, which include application resources, data, infrastructure. It also includes processes, such as development processes, operations processes, and identity and access management. So those will be what we usually have. Development includes CI/CD pipelines, version control. Operations includes monitoring, alerting, etc. So this is a collection of components and resources that are supporting a specific business process or a specific business functionality. So what we have here is a workload, and we usually have a workload team. So workload team for every workload supporting every different business process within the organization. So the workload teams would be the ones that primarily refer to the WAF, but they also need to understand what the CAF is so they can properly communicate with the central teams that will be guiding them and helping them in developing their workloads, for example, providing light landing zones, etc. The difference between workload and central teams is that in central teams we usually have very highly specialized roles. So if we talk about security, we have people that are highly specialized in cyber security. If we talk about operations, we have people highly specialized in operations such as incident management, monitoring, etc. So those are experts in each of their fields, and within the workload team, we have more of a multidisciplinary kind of team. We have roles where people understand the technology part, but they also have a very good understanding of the specific business process that they are designing the workload for. So both of the teams need to understand what the other is doing, and they need to be able to communicate. They need to understand both frameworks so they can communicate easily between each other. So the way that WAF is developed is we have the workload, and we also have the 5 pillars. So the 5 pillars, we can think about the 5 pillars as the non-functional goals or quality goals that will make our workload well architected. So Microsoft's point of view is that there are 5 things that are very important to get right. So reliability, security, cost optimization, operational excellence, and performance efficiency. So those are the 5 non-functional goals that we strive to achieve in order for our workload, our collection of components, supporting a business process to be well architected and optimally architected for the cloud. Across the 5 pillars, Microsoft has designed 4 sections. Under each pillar, there are 4 sections that repeat for all of the pillars. So we have, for all the pillars, we have design principles. So this is, for example, if we talk about reliability, what are the principles that we need to follow when we design so our workload becomes reliable. Security, same thing, we have high-level principles. Below the principles, we have more specific approaches as to what needs to be done in order to follow this principle. If we look at the different pillars or quality goals, we can see that there are certain conflicts. For example, if we talk about reliability and cost, workload that is more reliable will not necessarily be the cheaper. So we need to think about what are the trade-offs between each of those pillars. So under each pillar, we have a section talking about trade-offs with the other pillars. We also have recommendations. And the recommendations include design principles, essentially a collection of design principles that are appropriate for each of the pillars, as well as more specific guidelines or more specific methods to implement the design principles and the approaches under each design principle. And the 4th section that we have under each pillar is checklists. So the checklists essentially ensure that we have actually implemented all of the recommendations. They help us drive action and ensure that the people who are responsible for implementing all of this are actually doing it. So if I go to the documentation of the WAF, we can see, if we open here the pillars, we have, for example, reliability, and under reliability we have design principles. For example, design for business requirements. We have different approaches that we can follow. We have the trade-offs. So we have trade-offs between reliability and security, reliability and cost optimization, etc. Recommendations, which include the design patterns, and also standard industry design patterns such as Ambassador, Bowhands, etc. And we have the recommendations. So in this video, I'm going to talk about the design principles and the trade-offs in details. And we also have a few other things that are actually cross-cutting across those pillars provided by the WAF. So we have a cross-cutting guide on optimizing the workload using flows. So what this means is that we need to understand the different flows, or the flow is actually a set of interactions with the workload that happen during the execution of a business process. And having this understanding allows us to know which component and what are the places that we need to optimize. So there is a full guide, which I'm not going to cover in this video, on optimizing using flows, optimizing the workload for different pillars using the flows. We also have a full guide on health modeling. What health modeling is we take the monitoring data and we apply business context to it so we can have a better understanding of what is exactly happening when there is an incident, etc. It's also cross-cutting because it helps us across multiple pillars. Besides this, we also have WAF assessments. So I'm going to talk about the assessments in a few moments, but this is essentially allowing us to go through a list of questions and ensure that we're actually implementing everything within the WAF and gives us a score of about how well we're doing with implementing the WAF for workload. So those are the cross-cutting components. When we talk about a workload, there is the idea of workload classification. So Microsoft tells us a workload can be, for example, either mission critical, security critical, or it can be a hybrid workload, or IoT workload, or SAP workload. And depending on what class of workload we have, we can design around that and optimize around that. For example, we have the pillars here. Reliability, security, cost, operations, and performance. So if we have to look at what's the importance on a scale for each one of those things when designing a workload. For example, if we classify our workload as being mission critical, in that case, the reliability becomes the primary goal. So our importance for reliability will be high. We also have similar importance for security, cost, and security and operations and performance, because those essentially eventually affect the reliability. But cost is here where we'll be essentially giving less importance to. So we will be optimizing for reliability, and cost becomes less important on the scale. So the knowledge or the classification of our workload allows us to know how we should prioritize our pillars when architecting the workload, and those classification guides provided by the framework for the workload help us with that. So now I'm going to talk about the design principles and go through each of the design principles and explain what they are and try to give you some perspective about each of the design principles and how they're designed, how they're developed. So starting with really the reliability, design principles. So reliability is essentially composed of two things. Reliability is both the availability and the resilience of the workload. Availability meaning what percentage of time over a given period of time is the workload usable by users and other client systems. For example, 99% availability over a period of 1 year. It's usually directed by service level agreements with the customers, and in some cases you need to respect a certain percentage of availability. We also have resilience, which is how resilient our workload is to failures, and how isolated it is from dependencies that can cause failures, etc. So talking about the design principles for reliability, we need to start with designing for business requirements. We need to design for requirements. So this means we need to understand how is the workload going to be used by end users. What are the user experience expectations from the business? What are the workflows, etc. And we need to define or quantify success targets. When is the workload considered reliable enough? We also need to look at constraints. For example, if we try to make the workload reliable, in some cases we want to deploy it in multiple regions, for example, but we may have legal constraints that require us to only deploy within certain regions. So we need to understand what are the business constraints that essentially should guide our resilience design. So the next principle is actually designed for resilience. And in order to design for resilience, we need to start by looking at the critical path. So what is the critical path of components that a flow, so a business flow or sequence of interactions need to go through in order to achieve the business functionality we're looking for. We need to differentiate the critical path components from all the other components and focus on those when we're designing the workload for reliability. We also need to look at failure points. Are there any single points of failure? What can cause our workload to fail critically? We need to design self-preservation mechanisms into the workload, and also in some cases we want to over-provision. So we want to have more resources than we need so we can sustain certain failures or in some aspects of the workload without actually compromising the critical functionality of the workload. The next design principle that we want to follow is to design for recoverability or recovery. The way to design for recovery is to prepare recovery and disaster recovery plans. It's also designing self-healing features into the workload and looking at what are our recovery time objectives, recovery point objectives, and ensuring that we meet those. We also want to design for operations. If you think about operations, a workload that is difficult to handle during operation and production, it's a workload that's going to be naturally less reliable. So we want to ensure our workload is good for operations. For that, we need to design observable systems so we can have good monitoring on them. We want to simulate failures in pre-production and production. And we also want to build for automation. We want to reduce the amount of things that need to be done manually that may introduce human errors in the process. We also want to remove any redundant processes. And lastly, we want to keep it simple. That means keeping a lean critical path, writing just enough code, and using the platform provided features. So don't develop features on your own if something is provided by Microsoft on Azure, because that is what's proven to work well. We want to leverage that. Now moving to security. So the security design principles are actually derived from two frameworks that are standard in the cybersecurity industry in IT. Those are the Zero Trust model, as well as the CIA triad. The CIA triad is essentially we need to ensure the confidentiality, integrity, and availability of the data that we need to protect. So if we look at this, we see that essentially each of the design principles, each set of design principles are usually based on or derived from industry standard frameworks. They're not designed from scratch by Microsoft. They're just put together to help us design our workload with one self-contained package of design principles. So the design principles here is starting with plan for your security readiness. This means that we don't want to wait until an incident happens to try to figure out how to handle it. So we need to understand the security boundaries of our workload. So where does the security boundary stand for each of the components, the processes, etc. We need to do role-based security training. So depending on the roles that will be interacting with the workload, we need to train them appropriately. We also want to design an incident response plan, and we want to align this with the security operations center if we have one within the organization. The next three principles are directly derived from the CIA triad. So we have design for confidentiality. So in order to design for confidentiality, we want to impose strict access control. So we apply the zero trust principle by explicitly verifying the identity and the access rights for every person trying to use anything at any level. We want also to encrypt data in transit, at rest, and during processing. So those are the essential things to ensure confidentiality. For the next one next principle is designed for integrity. So for integrity, we make sure that, again, people are not tampering with the data. So we do need strict access controls like before for confidentiality. We also do need encryption, but we also need immutable backups. So we don't want people to be able to go and change something in the backups. We want them to be immutable and encrypted. And then we want to also design for availability. So we need to design our workload to take care of cybersecurity threats designed specifically to attack availability, such as distributed denial of service, but also in our effort to make our data available to the different clients within the organization, be it users or systems, we may tend to provide scope that is too large. So it's important that the access control scope is defined appropriately, so we don't give too much scope when not needed. And the last is design, so sustain and evolve your security presence. So So this is threat modeling, having a good understanding of what your inventory is, periodic security tests, and also security patching. Now, if we look at the design principles and how they're generally organized under each pillar, we notice that we have something that is usually that would usually be mainly a responsibility of a central team. So plan your security readiness. Yes, we want to plan our security readiness at the workload level, but there should be some general plan within the organization that we need to follow. This goes for all of the design principles for all of the pillars. So there is something we begin with something that should actually be coming from a central team if we have one within the organization. Then we have a few design principles that are very specific to that pillar, that are usually derived from the frameworks, standard industry frameworks. And then we have something that essentially implies that we should not just design once for this pillar, but we should be improving over time. So we have like here we have sustain and evolve your security presence over time. So this means that you need to do some things periodically in order to maintain this quality goal. This goes for all of the design principles for all of the pillars. So the next pillar that we're going to talk about is the cost optimization. So cost optimization principles, design principles, are derived from the FinOps framework. And the FinOps framework is a specifically designed framework for financial operations in the cloud. And it is an industry standard. If we look at the documentation, let me just open this. So the FinOps framework looks something like this, and it has it's a lot about financial discipline and understanding our usage of the cloud, etc., and governance. But if we look at we look at the member organizations, we see that we have Google Cloud, Microsoft, AWS, system integrators like Accenture. We have some companies that are specializing in cost optimization of FinOps like Virtuoso, etc. But the design principles are taken out from this framework, and they are the design principles that are important at workload level. So the framework provides design principles at organizational level that will be integrated within the FinOps central team, etc. But here we look at what is for specific for the workload. So the first principle is to develop financial discipline. Developing financial discipline is, yes, it's important workload, but again, it should come from the central team. Some guidelines should come from the central team. Then we want to design with the cost efficiency mindset. This also should be a shared responsibility between the workload team and central FinOps team within the organization. So to design for to develop a financial discipline, we need to start by designing our cost model. So understanding the total cost of ownership of our workload, as well as the different components, such as the cost of the resources, the cost of training, the cost of operations, etc. We also need to have a flexible accountability model within the organization. So we can ensure accountability for different parties that are involved with the workload. We need a budget and we need governance. Designing with cost efficiency mindset is we need to think about the total cost of ownership on the return on investment. We also need to take into account service level agreements. So some things will be required by the contracts we have with our clients. For example, we need to maintain certain level of availability throughout a given period of time. This is something that we need to take into account when we plan our cost. The next one is design for use optimization. So when we select resources on the cloud, we select a specific SKU of the resource based on certain features that we're explicitly looking for. For example, we want a memory optimized virtual machine on Azure, and we go and select that SKU that has more memory relative to the CPU. But there are other features that come with that SKU that we need to look at and try to see if they can be usable. Is there any value of using those features that come along with the SKU that can help us optimize our cost, our investment in that SKU? So this is use optimization, or are there ways to make better use of what we're actually purchasing from Azure? Are there any unused resources within the organization that we can take and use for that workload? Then we want to design for rate optimization. So when we purchase things on Azure, we can either pay as we need. So we can pay for something by a second or by the minute or whatever for the amount of time that we use it, or we can plan for using over a fixed term. For example, we say, okay, we'll need those VMs for 3 years, and then we can benefit from a lower rate that we pay for those resources. So we need to see, is there some baseline of compute resources, storage, etc., that we can use, so we can commit to a fixed term for those resources and get a significantly lower rate. There is also the concept of hybrid licenses with Microsoft and Azure, where we can use licenses, for example, for SQL Server or Microsoft licenses that we have purchased for our on-prem servers. And we can take those and have some cost savings when we use them on the cloud as well. So some of the licenses can be used on both on-prem and on the cloud, or just one or two, but Microsoft offers different options that can allow us to save from our existing licenses on-prem. We also need to look at regions. Potentially some of the regions that offer the same resources may offer them for less money, the same resource. So if we are not constrained by some regional regulations, we can take advantage of cost savings from different regions. So the last one here is essentially monitor and optimize over time. Just like the previous one, we don't stop with the initial design of the workload. So we look at different underutilized resources periodically. We look at how we can save money from different environments. For example, do we need the same thing in production as pre-production as development, etc. We need to optimize our environments, and we need to adjust our design decisions to meet our return on investment over time. So the next one is operational excellence. So the operational excellence design principles are mainly derived from the DevOps practices. So the first principle that Microsoft says we should follow to design for operational excellence is to embrace DevOps culture. Again, this is something that can be helped by our central team. We don't need to, if we have a central team within the organization, we don't need to take all of the weight of embracing DevOps culture at the workload team level. We want to leverage, if we can, whatever guidelines and practices are suggested by the central DevOps team. We want to have a good communication channel with the people within the central DevOps team and our workload team. So developing, embracing DevOps culture generally involves using common systems and tools, adopting an experimentation and learning mindset, and having a central operations team. So this is, as we mentioned, central development and operations should be leveraged to achieve this design principle. The next one is to establish development standards. again, this should come from our central teams if you have them. But we need to follow industry standard development methodologies such as Scrum or Kanban, etc. We need to use source control. We need to have appropriate QA processes, and above all, we need consistency between the different components within the workload. We don't want to do something for one of the components and do something completely different and inconsistent for other components. So the next one is evolve operations with observability. So it's not just the initial design. We want to continuously improve. We need to decouple modeling components from the critical path components within the workload. We want to establish consistency in the way we collect data. So we need to have a good understanding of the different types of data we're collecting. We need to have consistent storage locations where we store the data. And we also need to establish standards around the collection of data. So we ensure that we collect just enough data and we keep it for just enough time. So this data, if we think about it, it's a security risk among costs and other things to keep it for too long or keep too much of it. So we need good guidelines on what we actually need, what's beneficial for like improving and evolving our operations, and keep just that. So the next design principle is deploy with confidence. And in order to deploy with confidence, we need to adopt approaches like infrastructure as code. So, for example, we want to ensure that whenever we deploy infrastructure, is not done manually. We have the same deployment manifest that we can use. We also want to ensure that we use the same deployment manifests across different environments, not write different deployments for different environments. And also, we want to look at our infrastructure as something ephemeral that can be redeployed fast. And we don't want to, so it needs to be immutable and looked at as ephemeral. So we don't want things to be changing while it's deployed. So we don't want people going in and manually adjusting things that are not in the deployment manifests. We want to make sure, we want to have this confidence that when we redeploy from the manifest, it will be the same thing that was what was just destroyed. So we want to be able to destroy it and redeploy it easily and with confidence. So the next one is we want to design for automation. So if you think about it, the less automation we have, the worse the experience would be in doing things on the workload, and the more chance there is for human error. So just like with deployment scripts for infrastructure, we want everything, every aspect, every tier of the workload, including the application layer, data layer, and infrastructure, to be automated. We want to remove redundant workflows, and we want to design our components in a way that they support automation. So this can be easily done. And last one is to adopt safe deployment practices. Safe deployment practices. So we need to consider different deployment models that we can use, such as blue-green deployments, feature flags, canary deployments, in order that we control the blast radius of anything wrong happening. We also want to deploy in small increments following the DevOps best practices, so we can reduce the number of issues that we can potentially have with each deployment. We also want to have a mitigation strategy, so we should expect that something will go wrong from time to time. We should know how we'll mitigate it upfront, and we should also have fallback plans so we can fall back to our working condition whenever something goes wrong. Those are the design principles for operational excellence. Now, the last one that we need to go through is the performance efficiency. So those are the performance efficiency design principles. So when we think about performance, the first design principle is we want to negotiate realistic targets, performance targets with the business stakeholders. So negotiate realistic targets. Okay, let's notice this. It's performance efficiency, not performance at all costs. So we don't want to over provision. We don't want to spend too much on performance if not needed. So we need to look at different what would be the realistic targets that we need to establish with the business, and for this we need to prepare. So we prepare for negotiation. We look at different options, different ways to design the workload that can provide different performance criteria, performance specifications. If we have historic data, have done something similar in the past, we can look at that. If we haven't, we can also look for external sources such as research, etc., from outside of our organization. We want to collaborate with the business owners to properly define those targets, and we want to identify the flaws, just as we do for the reliability. We want to know what are the flaws of interaction the users will have with the different components within the workload, what are critical paths, so we can optimize for those things within the workload. And we also want to develop a performance model. The next one is we need to design to meet performance requirements. So design to meet performance requirements. So we need to do capacity planning, determine what are our targets, choose the right resources for the workload, and do proofs of concepts to ensure that we can actually meet the requirements, that we can meet what we have committed to with the business stakeholders and with the public or whoever our clients are. Then the third principle is achieve and sustain performance. So in order to achieve and sustain performance, we want to develop a performance test that we do periodically. we want to formalize those performance tests, and we want to use them as quality gates whenever we deploy something new. So we have the workload designed. We need to do changes to it. We have some performance test that we can run as a quality gate to say yes or no, the workload, the change can move on into production or not, so we can sustain our performance that we have achieved. We also need a repeatable monitoring process, meaning that we can reliably monitor our performance. We know what to monitor, what is important to look for performance. And the last one is improve efficiency through optimization. Improve efficiency through optimization. So we don't just design this once, as we said. We want to do periodic cycles to look at to review the efficiency of our workload. So yes, we have a performance, we sustain a performance, but we want to make sure that we're efficient in how we're getting there. So we analyze historic trends. We look if we have enough or not enough performance. We look at potentially redesigning using better design patterns or more appropriate design patterns depending on what we see, and also look at potentially for new components that we can use within Azure. So sometimes we will have new components, new SKU variants that provide different features and maybe better suited for what we need in order to increase our efficiency in how we get the performance that we need. So those are the 5 pillars and the design principles for the 5 pillars. So let's talk about trade-offs. So trade-offs are essentially balancing the needs between each 2 pillars. If we think about reliability, starting with security. There are things that we're going to do in terms of increasing our availability, for example, putting our components in an availability group. So if you have one component alone, our surface area of attack looks something like this. But if we put this component into an availability group, where we have 2 or 3 of this component, and then we have a load balancer distributing traffic between 3 components, then our surface area of attack increases with this. So when we do things to improve reliability, we have usually increased surface area of the workload that will negatively impact security. We also may need to bypass some of the security controls that we have in place. So if you think about it, there are security controls at different places. For example, in CI/CD pipeline stages, you have scanning of the code, etc. In terms of who is reviewing your pull requests before they move to production, you have different roles and different people involved. All of those are different security controls. And we need to balance the need for those security controls. Bypass. We need to balance the need for those security controls with reliability, because there will be moments where you need to, for example, push a bug fix to production in order to quickly fix something that's causing downtime. And in that case, yeah, you may have security controls that prevent you from doing this in a timely manner, and you may need to bypass those security controls for making sure you meet your SLAs, etc. Um, there may be legitimate reasons to do this. The idea is that you need to balance the need for security controls with reliability. You may also be tempted to keep old software versions. When you want more reliability for your workload, because usually proven older versions will be reliable in the sense that they work well with your dependencies. You don't introduce any breaking changes. You know that it works, don't want to change it. But security requires you to do regular security patching, etc. So then there's those things to balance out. If we think about the security side, on the other hand, there is an increase in complexity. So instead of just having a workload or a workload component, now we have other things that we're adding, such as Active Directory to do identity and access management. We can add a key vault to store our secrets instead of keeping them inside the code. All of those things increase complexity, and as we said, for reliability, one of the design principles is keeping it simple. So increasing complexity has potentially a negative impact on reliability. This needs to be balanced out. We also introduce an increase in critical dependencies. So all of those additional components that are strictly there for security purposes introduce failure points, which can eventually add up to downtime and reduce the availability of our workload, or can reduce the resilience of our workload. And on the contrary to reliability, as we said, we want to do changes, regular changes, which can introduce instabilities in the workload reliability. So the next pillar we want to compare against or to balance against is the cost optimization. When we add all of those components that we just mentioned, such as load balancers, availability zones, additional regions, backups, etc., we obviously increase the cost of implementation of the workload. We also need to increase our investment in operations that are not aligned with the business functionality of the workload. So that's one in operations not aligned. Functional requirements. If we think about the cost side of the things, trying to reduce cost will obviously have an as effect to reduce our resiliency, to reduce our availability, because we're trying to save on those component redundancies that we would have, for example, if we have availability zones in multiple regions, etc. We also may limit our recovery strategy. One example of this can be if, for example, you want to have active regions for the workload where both are active at the same time. If one fails, have zero downtime, you just need to switch all of the traffic to the other active instance. Trying to reduce the cost may require you to have an active passive implementation where one of the instances is only activated, one of the primary instance fails, or the primary region fails, which will cause some downtime, which reduces availability and has a negative impact on overall reliability. So those are the considerations, some of the considerations for cost optimization. The next one is operational excellence. So when it comes to operational excellence, our reliability design patterns that we introduce obviously increase our operational complexity. Obviously, this increases the requirements for more automation, it adds operation workflows, etc. So overall, the experience and the potential to make mistakes, misconfiguration mistakes, or other human mistakes while operating the workload in production increases. So we need to keep this in mind. There is also increased effort to generate team knowledge, training requirements. Obviously, working with different reliability design patterns requires our operations team to upskill to better understand those patterns, etc. If we think from the operational excellence side, we also do things that increase complexity, but for the operational sake, so increase complexity. And as we mentioned with other pillars, increased complexity has a negative impact on reliability. We want to keep things simple for reliability. When we work on our operational excellence, we do things like automation, infrastructure as code, and other things that can become very complex. So you can have different manifests at different levels of the workload, different tiers of the potential for misconfiguring something increases, which will obviously downgrade our reliability. And we also can introduce an increase in destabilizing activities. So we do things like synthetic traces on the workload in production for monitoring, etc., which can have a negative impact on the workload itself, so on the reliability of the workload. So the one left to compare with reliability is the performance efficiency. So from the reliability side, what we do to affect our performance is, again, we introduce things like load balancers. Those load balancers add latency in the workflow, in the flow of information from point to point. So we do different things that add complexity, and by consequence, they increase the latency of the network traffic. We also, for reliability's sake, may over-provision in order to protect ourselves from things that can reduce our availability. For example, we can add more capacity than we actually need, which has so we have over-provisioning possible. Which will affect our efficiency in the performance efficiency goal. So we may have increased performance as a consequence of adding over provisioning, but we have it at a lower efficiency cost. So that's something to consider when balancing between performance and reliability. If we look from the performance side, we can also do things that increase complexity. For example, adding content distribution networks, so we can have faster access to data from different regions in the world. We can do caching, we can do different things that increase, in general, the complexity of the workload in order to increase performance, which obviously has an effect on the reliability, which can be negative. We also want to do testing, so performance testing, as we mentioned earlier. We want to do a regular performance test to ensure that our performance is where it needs to be. This is done against our production environment, which can be an issue for reliability, since we're adding things as such as synthetic traces to check response time and everything, and this can obviously affect our reliability of our workload. Performance testing. We need to be careful how we balance between testing and what we want for reliability. So now we're done with reliability against everything. Let's look at the security. So security against cost optimization. So for security, we do add additional infrastructure. As we say, we have those key vaults. We have Active Directory. This increases infrastructure requirements, which obviously has effect on cost. We have to pay for those things. We also increase the costs because we add additional processes for security. Think about all the security checkpoints that we introduce, having different people approve our workload for security approve our changes before they go into in production. those are all things that we need to consider when we balance between security and cost optimization. So when we think about cost optimization, the cost optimization side, we want to reduce our costs, so we may be tempted to, we may have to reduce our security controls. For example, having less people reviewing the changes, etc., or having less scanning of the workloads before they go to production. We also may need to reduce segmentation. So one thing about security is we want our components as much as possible to be segmented, to be running on their own infrastructure, not to be co-located with anything else. But this has an increased cost. So if you want to reduce cost, that may have as an effect to reduce the segmentation. Or segmentation strategy that we're trying to maybe trying to implement from security perspective. So those are the things that we need to consider when we think about security versus cost optimization. The next one we need to look at is security versus operational excellence. So security can introduce complications in observability and serviceability. So introduce complications in observability. And serviceability. If we think about operations, we want to be able to monitor everything. We want transparency, and so we can easily diagnose any problem that may occur. But with security, we want to encrypt everything. We want confidentiality. So there are those two aspects at play that we need to balance between those two pillars. So the other thing is we decrease our agility. So as we mentioned, it's slower to push a change to production. It needs to go through more quality gates that include security. It needs to potentially go through more people. Traffic needs to be monitored, etc. So there are those things at play. If we look at operational excellence versus security, so we increase the surface area for potential attack. So just like with reliability, we add components that are not part of the functional requirements of the workload. We add those components for example, for monitoring, for observability and serviceability. For example, we can collect data somewhere for monitoring, data from logs, data from different telemetry and metrics, and this data becomes another thing that can be attacked, that's exposed to potential security risks. So We also want to reduce segmentation. If you think about it from operational excellence perspective, it's easier to operate run something in operations if it's not segmented among different infrastructure components. It's easier if everything is in one place essentially. So if we strive to achieve operational excellence, this can reduce our segmentation, which can negatively impact our security. And finally, looking at performance efficiency. So, doing things for security, such as scanning traffic packages and things like that, will have negative impact on performance by increasing latency. So this is one of the things that will happen. Then because security introduces complexities such as looking for secrets, for example, in key vaults, etc., we can increase the chance of misconfiguration. So misconfiguration, one example of misconfiguration where we can affect performance because of security misconfiguration is, for example, we put a firewall, we scan traffic, but if not all of this traffic needs to be scanned, then we affect performance for no good reason. So there may be misconfiguration in how in what we scan. We may be scanning things that we don't need to scan, which can affect performance. Those things need to be taken into considerations, and we essentially can introduce this degradation of performance if we try to do too much in terms of security. If we look from the performance efficiency side, then we may want to reduce security, so reduce security controls. So on the opposite side of what we're doing for security, we want to decrease latency, we decrease some of the security controls we have in place when we design, and we may do things for performance that will increase the surface area of attack again. We come to this again, so we increase the surface area of the workload. Again, that's with auto-scaling groups, load balancers, etc. So let's do cost optimization. Versus operational excellence. So the effects of trying to reduce cost can be, for example, compromised software development life cycle. So if you think about the SDLC, we have different things that we need to do, such as automated testing, managing our technical debt, etc. There are different best practices to follow that we want to integrate in our SDLC that we follow. But trying to reduce cost can compromise some of those practices. For example, you try to reduce the number of tests that you code. You try to leave some of the technical debt for later. You don't do regular cycles of reducing technical debt. So all of this can lead to reduced operational excellence. Something else that we can do in terms of degrading our operational excellence because of cost is reduced observability. And designing for observability is one of the principles for operations, but observability requires monitoring, it requires collecting data. This data needs to be stored somewhere. The storage costs some money, so trying to reduce cost will affect our operations in terms of observability. On the operational excellence side, we do things that increase our spending related to operations. So it's spending that's not related to functional requirements. Increase operational spending. We also increase the tooling demands. So all this observability, serviceability, automation requires additional tooling, and this additional tooling costs money, so it negatively impacts our cost. So we need to balance those things between cost and operations. So looking at performance efficiency, so things we can do to try to save money is, for example, under provision, under scale. So, for example, if we have scalability groups, outscaling groups, we can put a lower limit on the maximum number of instances that we want. Those are things that can affect our performance, and we can also stop doing optimization over time, or we can decide not to do optimization of performance over time, which is one of the principles for improving and sustaining operational excellence performance over time. So on the performance side, we can over provision. So obviously, it's better for performance if we have more capacity, more CPU, more RAM, more memory, etc. We can also add more components, increase number of components. Such as load balancers for autoscaling groups, etc. All those things will impact our cost, will increase our cost. So they need to be balanced. So now what is left is operational excellence. and performance efficiency. So when we want to do some things to improve our operations, we increase our use of resources. So think about the resources or the capacity that you have for your workload, available for your workload, as a finite kind of number of resources. Not because you cannot expand your number of resources or amount of resources in the cloud, but because you have a certain budget for this workload that you need to respect. So you will use some of those capacities, some of those resources for your functional requirements. And whatever you use for your operations, it's taking out of those resources. So if you use storage for storing monitoring data, if you use compute for different things related to operations, you're taking some of the budget you have for your resources, which may consequentially reduce what you have left to ensure your performance. You need to balance those things out. The other thing is that when you introduce certain things for operational excellence, you can end up increasing your latency. Think about, for example, synthetic traces to simulate user interactions with the workflow. Those can add to the load that your infrastructure needs to handle and consequentially reduce your performance at certain times. There are different things that you can do operationally. You can for example, try to access APIs, etc., in order to do monitoring and things like that. And if we think from the performance efficiency side, the way we can affect operations is we can increase complexity. By introducing additional components, for example, like load balancers, etc. Or we can do things that cause cultural stress within the organization. So think about, for example, root cause analysis, trying to understand why is the workload not performing as it's supposed to perform, looking at the specific components, who caused the issue, what the root cause. It can stress it can stress your different people in different positions working on the workload, which is against the operational excellence culture, which actually requires no blame kind of culture when we analyze an incident post-mortem, etc., and when we do cost analysis. So those are the things that we need to balance between operational excellence and efficiency, and this is the last thing that we are talking about in terms of trade-offs. So the last thing I want to cover as part of this video is the assessment section. So if we go to Microsoft Learn, we have different assessments, and if we come to the Azure well-architected review, we can start assessing for our implementation of the well-architected framework. It allows us to link a subscription or the subscription where our workload is located, so that we can keep trace of the assessments that we're doing with regards to that workload. Here it lets us select if you want to do a core review or if you want to do a review for specific component implementation. So if I go with the core well-architected review, I am asked to select which ones of the pillars I want to assess. Let's say we take reliability. And it's going to ask me a number of questions, such as do we have a deliberate goal to keep our workload simple? Do we utilize platform functionality where appropriate, etc.? So depending on what I select, and those are all of the recommendations that we had for implementing the design principles for reliability. Depending on what I select, I'm going to get a score in the end. And if I link the assessment to my subscription, I'll be able to monitor over time how well I'm doing and use those assessments as milestones. So I can do them multiple times, and I can see how my score is improving over time. So those are all the sections. There is one last that I didn't cover, which is service guides that are for specific components of the framework. Those really specific Azure components, you can look into that. But this is more of a collection of links to where to look for specific information for each of the components. So this is all about the WAF for now. I hope you enjoyed this video, and see you in the next one.